Greetings and welcome, internet friends. This is part 2 about properties of radicals and stuff. And so we've already seen some of these things in previous sections from previous books, but it's kicking it up a notch with a little bit more complexity. And so here we go. Radical expressions with the same index. So same index. Remember that in this case is the little tiny adorable number out in front of the root. I almost said square root. It would have been wrong. I would have been wrong. And the same radicand. And so the radicand are the numbers on the inside of the radicals. Oh, these ones are going to be a little bit more interesting. We call those like radicals. And to add or subtract like radicals, use the distributive property. Yeah, that is what's technically, that's one way to think about it. I'm just gonna say combine like radicals, right? Just like we used to combine like terms back in the day. If I have 2x plus 5x, that was 7x. Same idea. So for here, example 5, part A, I've got the fourth root of 10 plus 7 fourth roots of 10. This, I would point out, is 1 fourth root of 10, and here are 7 fourth roots of 10. And so I'm just going to combine those quote-unquote coefficients. That's not quite what they are, but there's a total of 8 fourth roots of 10 left over. Tell you what, now you might say, Mr. Waddy, there are no radicals in this one. But that's where you're wrong, Junior. We can reimagine a whole new world in which those rational exponents become radicals. And so here we go. So we'd be able to write it this way, right? Where the denominator of the exponent becomes the index of the radical. And if I've got 2 fifth roots of 8 plus 10 fifth roots of 8, how many fifth roots of 8 do I have? 12 fifth roots of 8. Excellent. Tell you what, let's go back and put a box around this one too. Dunzo. Now you might say, Mr. Waddy, these are not like radicals. Yes, they have the same index, but their radicands are different. And you are correct. However, this part right here is not a fully simplified radical. I believe I can find a perfect cube that will go into 54. And so I believe, tell you what, let's write some of those down. So because this is a cube root, I should think about the perfect cubes. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 125, etc. And I believe that 27 goes in to the 54. And so I'm going to break that apart, and that'll be the cubed root of 27 times the cubed root of 2 minus this cubed root of 2 still hanging out. Hey, you're starting to see where those like radicals are going to be. The cubed root of 27 is 3. And so I've got 3 cubed roots of 2 minus 1 cubed root of 2. And if that 1 wasn't there, you would still be careful and attentive to include it, at least mentally. And so 3 take away 1 is 2 of these cubed roots of 2. No es más mal. Let's keep going. So yeah, here's a 1, so that would have been 6 fifth roots of 12. This one I would have broken up into the cubed root of 8 times the cubed root of 5, because 8 times 5 is 40, and 8 is a perfect cube. And then I would have had plus 2 cubed roots of 5 with this other cubed root of 5 hanging out. I had ditto marks right there. So 1 plus 2 is 3 of those cubed roots of 5. Thing of beauty. By the way, 9 to the 2/3 power is the same as the cubed root of 9 all squared. You also could imagine that as being the squared on the inside, if you wanted. And so that's actually the same as the cubed root of 81. And so yeah, so you could simplify those to be that way. And actually, cubed root of 81, we technically could have broken down in a cubed root of 27 times cubed root of 3, and simplified even further. I didn't do this whole problem. I was just chipping away at the inside part, the part that I thought would have been interesting. All right, so check this out. Be forewarned, on currently my version of Algebra 2, the upcoming test for this unit, I'm not going to require you to include whether or not you need an absolute value over these x things. But there will be some homework problems about this, and it may show up in future courses, so be forewarned. But it turns out properties of rational exponents like radicals can be applied to some expressions involving variables. Because a variable can be positive, negative, or 0, sometimes absolute value is needed when simplifying a variable expression. Now notice this. If my index n is odd, right, 7 is odd, and I want to cancel this out with that, that's just equal to plain old 5. All right. If I cancel it out with that, that would equal negative 5. Excellent. Very good. Very good. Now, if I have n being even, such as 2, 4, 6, 8, it does work if the inside, the radicand's base, I guess, is positive. That works just fine. But be careful right here. If my inside had a negative that was being raised, and so we're imagining that this is a variable, which we already said could be negative, these would not cancel out, and that would not equal negative 3. It would actually always equal the absolute value of whatever this number is. And it won't always look negative, right? The y here looks positive, but remember, y itself could represent a negative number. And the reason this will always equal the absolute value of that is because I'm raising that negative 3 to an even power. And remember, that means negative 3 times negative 3 times negative 3 times negative 3. There we go. My dots aren't showing up there. And that would be a total of 4 negatives, an even number. And so those minus signs would pair up and become the best of friends, go on adventures together, possibly a road trip, right? Yeah, they're all hanging out, having a great time, and everyone becomes positive. And so even this negative here would become positive, and then the fourth root would have brought it, right, canceled out with that part and brought it back down to the 3 size rather than whatever 3 to the 4th power is. So be careful. If I am reducing a radical with an exponent over a variable, and if the index is even, you gots to have that absolute value. And here's a little fact, absolute value is not needed if the variable is assumed to be positive, which some of our later examples will allow for. All right, and so let's break this up. Cubed root of 64. I'll tell you what. Now cubed root of 64 is 4. So I'd be able to simplify that. I'm gonna break this up. So notice this. I would have cubed root of 64 is 4. The cubed root of y cubed, those are both odd. Yeah, I'm only breaking this up in order to apply that rule that we were just looking at. And the way they defined the rule, both of these were the same. And so that's why I was trying to be careful to honor that particular presentation. But here we go. Cubed root of y cubed, because 3 is odd, I can just write plain old y, right? Those would cancel out, and just plain old y would be left over. Whether y is positive or negative, who knows? And this one cancels out, and I would get plain old y. Now, y times y is the same as y squared. And notice, well, actually a couple things going on here. If y was negative, then y is still negative here. If this y was negative, because they're the same y, then this y is still negative, and a negative times a negative ended up being positive anyway. It ended up working itself out. Now, there is the way to take a look at this and just divide if it is divisible, and notice that would give me the 2, and as long as I'm still looking at whether or not this is odd or even, odd is going to tell me that no abs needed. All right, no absolute value is needed on the variable down here. And so, yeah, that there could have been a shorter way to do this problem where I could have actually just jumped right to this last step, since we've got that working. Let's rewrite this one. So 4th root of x to the 4th over the 4th root of y to the 8th. One thing to be aware of, right, is that I can distribute a radical over multiplication or division like I did here. And so according to this new thing, because the index is even, therefore absolute value is going to be needed. Abs val. And so the 4th root of x to the 4, those cancel out, but I'm going to write that as the absolute value of x. The 4th root of y to the 8th, this is where I'm going to use my little divide trick. 8 divided by 4 is 2, and so that's y squared, and I'm going to need the absolute value. But wait, this absolute value is redundant, meaning it's unnecessary. Now, let me explain why. Why? Yeah. Because y is being squared, even if y is negative, squaring it will make it positive, and then so I no longer need the absolute value. The x will still need the abs val, but the y will not. And so, so here we go. So here's the simplified answer, assuming positive, negative, or 0 values for our variables. Tell you what, I'm going to write my little divide trick here as well. Divide. There you are. There you are. Okay. Now notice this, and immediately we walk away from that. Let's just say, let's just pretend all of them are positive anyway. Oh, okay. So let's break this up. So 5th root of 4 times the 5th root of a to the 8th, I want to point out, is not divisible by 5. But the largest number that is divisible by 5, that could fit into 8, is 5. And so I'll have a to the 5th times a to the what would combine to be a to the 8th? Well, 5 plus 3, because I'm considering the property of exponents, where if I multiply a to the 5th times a to the 3rd, I would add the exponents. All right, and so you notice that's how I've got this set up. I'm actually super sad. I'm going to run out of space so fast. Guys, I'm running out of space. All right, let's keep going. As far as b to the 14th, the largest divisible by 5 number that I could break that into is b to the 10th. 10 is divisible by 5. And so I'm going to write this as the 5th root of b to the 10th times the 5th root of what's left over? Well, 4 is, because 10 plus 4 is 14. And c to the 5th is already something that's divisible by 5, so I'm just gonna, it's able to reduce with a 5th root. And so I'm gonna write, Charlie to the 5th. There we go. All right, so let's, the first thing I'm gonna do is I'm gonna take all of the ones that can simplify. This one, and this one, and I'm gonna write those out front. So the 5th root of a to the 5th is a, the 5th root of b to the 10th is b squared, and the 5th root of c to the 5th is c. So I've taken all of those, the ones that actually cancel, and write them out front. And then I'm going to combine all of the irreducible ones and write the fifth root of 4a cubed b to the fourth, because those were unable to be reduced. And since I was assuming all variables are positive, I didn't have to consider whether or not absolute values were showing up on these things. Okay, let's take a look at this next one. And I'm sad because now it messed up my work. All right, x over the cubed root of y to the eighth. So what's the largest exponent that goes into 8 that is divisible by 3? I believe that's 6. And so I'd have the cubed root of y to the 6th. All right, this is the saddest looking. All right, I'm doing whatever. Times the cubed root of y to the what? Okay. So y to the 6th times y squared would equal to y to the 8th. That's there. Pardon my poorly placed work. Okay. So up top, I'm gonna. Oh, this problem's devious, guys. Deviousness. The cubed root of y to the 6th is y squared, because I divide the exponent by the index. And I'd have the cubed root of y squared. Now it says simplest form. Guys, I can't leave it in this form. Does anyone know why? You guys are all shouting it at the top of your lungs out of your windows as you're in, you know, your self-inflicted quarantine sort of thing, your stay-at-home order. Well done. Much respect for you. Thank you. But you're all saying you can't leave a radical in a denominator, and you're correct. You are correct. And so I've got to multiply this by something that's going to get rid of this radical in the denominator. I'm going to multiply by some version of a cubed root. All right, and whatever I multiply by, it's got to be the same thing over itself so that the whole thing is equal to 1, and I'm not changing the value of this. So what do I multiply y squared by to give me something that would cancel with a cubed root? Well, a y to the first, because y squared times y to the first will give me a y cubed. Let's see, I think I'll have just enough room. So up top, multiplying across, I'll have x times the cubed root of y over y squared times the cubed root of y cubed. And as a result, I can cancel this out, and I'll have, what, y squared times a y to the first will be left over. Oh dear. Guys, this is the saddest arrangement of work you've ever seen. And final answer, yeah, it will be. X times the cubed root of y, up top, y squared times y to the first is y cubed. There we go. Final answer on that one. And I do want to point out that notice you can't reduce this and this because this is inside of a radical. This is not. If they were both inside of a cubed root for some reason, then yeah, then you'd be able to do your normal reducing stuff. Okay. Guys. All right. Let's rearrange this. 14. Let me give myself some space. 14x, I'm going to rewrite that as the cubed root of y over 2x to the... let's write that as the fourth root of x cubed. All right. And z to the negative 6, I'm going to move that upstairs. So that's z to the positive 6. All right. So let's see. What can I simplify? Well, I can't leave this radical here. It looks like now both of these are outside of radicals, so I can cancel that normally. 2 goes into itself once and into 14 7 times. So that's, remember when reducing fractions used to feel complicated? Well, have I got these math problems for you? Yeah. Let's see. So what do I have? How do I get this radical out of the denominator, guys? Well, I'll tell you. I'm going to multiply by a fourth root over a fourth root. I'll tell you that much. And this is an x cubed. So how many x's do I have to multiply that by in order to give me an x to the fourth? Something that would be divisible, say, by 4. And I believe that's just an x to the first in this case, because 3 plus 1 is 4. It's going to be great. So 7x times, tell you what, I'm going to put the z next. I like to write the cubed roots last, or any radicals last in an expression. This canceled out, it's just 1. 4th root of x to the 3rd times 4th root of x to the 1st is just plain old x. Well, it would have been the 4th root of x to the 4th, which is x, okay? But to save some space, we'll write it that way. And time, space and time, space time. It's 20 minutes video, yikes. All right, and so this is what I would get. Now, can this denominator cancel out with anything? Well, yeah, because both of these are, none of them are in a radical. They all have the same quote-unquote index. Yeah, we can actually cancel this out normal. You also could have done your properties of exponents trick, where you'd be like, oh, I'm going to subtract this one here, and that'd be x to the 1 minus 1, which is x to the 0, which the whole thing equals 1. And so whether you cancel it out or do your property of exponents, final answer, 7z to the 6th times the cubed root of y. Okay, I was like, did I have any y's that were outside of a cubed root? But no, I didn't lose anything along the way. All right, good. Last question. Yep, once again, let's just pretend variables are positive. And hey, this is combining like radicals. 5 and 6 is 11 square roots of y. That one's easy. Now over here, well, I see a couple options. This first term, kind of, it's not quite a term, is 12 times the cubed root of 2, and I'm gonna break the oh dear, my 2's and my z's are gonna look so similar. Forgive me. I'm gonna break z to the 5th into z cubed times z squared. And so the reason I'm doing that is because this one can be reduced, whereas in that form, right, it didn't look like it. And this one definitely can't. Okay, minus. Now for this part, I've still got z outside. I've got the cubed root. 54 I can break down. I think we did, yeah, 27. We already did that earlier. Times 2 is 54, and the cubed root of 27. 27 is so nice because it's a perfect cube, okay? That's why I'm picking that number, just so you're aware. So yes, 3 goes into it. Yes, 9 goes into it. But I'm picking 27 because I'm picking something that's going to cancel with the cubed root. And then let's see, z squared I can't do anything with. So let's simplify. 12 cubed root of z cubed is z times the cubed root of, let's write everybody who's left over on the inside. That's 2z squared minus cubed root of 27 is 3. This z is hanging out. Be careful. This is not an exponent to the z. It's an index to the radical. So the cubed root of 27 was 3. Multiplying this plain old z on the outside times the cubed root of 2z squared. Man, my 2's are looking even more like z's. And so let's see. Notice, cubed root of 2z squareds, those are like-ish terms. And so what do I've got? I've got 12z minus 3z is 9z times the cubed root of 2z squared. All right, you made it to the end of the video. I hope you have a great day. Go play with Minecraft Legos. Take care.